Okay, we're going to go ahead and get started now. Thank you everyone for joining. This is the Network Operations 2 session. My name is Jeff Kleinen from Netflix. I'll be moderating this session. The speakers we have today, Amit. I won't pretend to be able to pronounce the last names for everyone, so please forgive me for just addressing your first names. Amit from Colt. He'll be talking about the network evolution for the Colt network. We have Andre from Nick CZ, the Czech Republic Nick. He'll be talking about the bird routing daemon. And lastly, we have Eric, the slides said, the website said Eric will be presenting, but his colleague Christian will be presenting in his place from Interland IX. He'll be talking about the TVX multicast exchange point over the Interland infrastructure. So, okay, we can start off, Amit.
Good afternoon, everyone. My name is Amit. I'm from Colt Technologies. We are a global service provider operating across Europe, UK, US, and in Asia. We offer packet, optical, and voice services in our network. And today I'm going to talk a little bit on the seamless network evolution we did for our new packet network using latest next-gen technologies like segment routing, EVPNs, and network function virtualization, and so forth. So this is a brief agenda of my talk today. I'll talk briefly on the history of our legacy IP MPLS network, then our vision towards one global converged packet network. Finally, I'll talk about some details on how we build the new network using latest next-gen technologies. And in the end, I'll share some of the experiences and key takeaways from our deployment. So on the history of our legacy IP MPLS network, so we have two networks. One is IP network, and the other one is the Ethernet network. Both are separate network with separate infrastructures. On the IP network side, we offer services like internet services, and then MPLS layer 3 VPNs, which include unicast and the layer 3 multicast services. So what we run on the infrastructure side of this network, we run ISS as our IGB routing protocol. We use MPLS LDB as our normal transport protocol, and all services runs on BGP protocol. We are AS number 8220. Similarly, on the Ethernet side of the network, we offer services like Ethernet point-to-point, Ethernet multi-point, and E-trees. And on the infrastructure of this network, we run OSPF as our IGB routing protocol. All services are RSVP-based, which essentially means traffic engineering. And we run TLDP-based, pseudo-wire-based solutions in our network for Ethernet services. So our vision is towards one global converged network, and we want to integrate the network from services, system, and process point of view to offer innovative services and to reduce the provisioning time and to automate our end-to-end orchestrator so that we can offer truly combined network services. And in the technology space, we are looking for a converged network, a network where we can achieve service flexibility, which essentially means that we can route some services via the shortest IGB path cost. And on the other side, we can leverage features like traffic engineering. We are looking for a network with simplified design and architecture, which means that we want to run less number of control plane protocols on this network. Plus, on the other side, we want to offer more and more services features on this new network. We are looking for a network with simplified design. We are looking for a network which is highly efficient, scalable, and a resilient network. And it must support network function virtualization so that we can virtualize various important critical network infrastructure components. So finally, based on these goals, we form our end-to-end converged network. So this is our new network at a glance. So it's indeed a converged network. So what we run on the infrastructure side of this network, we went with ISS as our converged IGP. So we have chosen ISS or OSPF considering some of the benefits of ISS, especially its support of TLV, where it can adapt to new changes for any new changes within the protocol rather than changing the complete protocol structure itself. We went with segment routing for any unicast services on this network. And we went with RSVP, which is required for layer 3 multicast services, because at this stage, segment routing doesn't support multicast services. And BFD for our normal fast failure link detections. And on the service side of the network, since it's a converged network, so obviously it supports all services on a single infrastructure. So on the Ethernet side, we introduce EVPNs, EVPN point-to-point, EVPN multi-point, IP services like internet services, and layer 3 VPNs. And on the multicast, we have next generation multicast, which is essentially an label multicast, and our deployment is based on RSVP P2MP based tree-based solutions. Let me talk briefly on the evolution we did on the MPLS side. So on the IP network side, we rely heavily on the LDP we use LDP as our control plane protocol, and the MPLS applications are L3 VPNs, which includes VPN v4s and VPN v6. So VPN v4s are deployed using 6PE. So VPN v4 include L3 VPNs include VPN v4s and VPN v6. So our VPN v6 deployment is based on 6VPE. And similarly, internet services, we use native IPv4 unicast, and we use labeled IPv6 unicast. So we don't have any native IPv4 infrastructure, and we carry v6 services over the v4 infrastructure using legacy techniques called 6P and 6VPE. And our network is built in such a way that we connect with most of the peering point IXPs all across the Europe and UK. And we follow the hot potato routing in the network, which essentially means that traffic will exit via the nearest peering point. So we rely heavily on the IGP metrics. That's why we have LDP on the IP side of the network. Plus we have various other applications like L3 VPNs. Convergence is one of the main requirements, where LDP can provide fast convergence by means of LDP FRRs, LFAs. And we have a lot of ECMP paths in the network, so we used to upgrade capacity regularly, and where LDP can support ECMP path without any problems. On the Ethernet side of the network, we use RSVP as our MPLS control plane protocol, and MPLS applications are VPWS and VPLS. So VPLS is essentially a multi-point Ethernet services. The reason why we have RSVP on the Ethernet side of the network is, one, we offer a feature called disjoint paths to our customer, for which we have to do traffic engineering. That's why RSVP is required. Second is that we offer very strict SLAs to our customers. So be it any failure in the network, node, link, SRLG, and so forth. So we need to ensure 100% protections. That's why we have RSVP on the Ethernet side of the network. Certain challenges we faced with our existing MPLS design. So on the LDP side, the biggest challenge as an operator we face is on the coverage issue. Though LDP can provide fast convergence, so 50 millisecond without any problems, but there are certain shortcomings from the coverage point of view. So LDP-based network depends upon heavily on your IGB metrics and the topology used. So based on that, coverage result varies. Again, there's a lot of evolution happen in this space. Earlier, there was just directly connected LFAs, and then later on, remote LFAs were evolved. So protection improved significantly, but again, it never reached 100% because remote LFAs depend upon the concept of a PQ node. So if you have a PQ node in the topology, means you are protected. Otherwise, same sort of problems are there. Second problem with LDP is that it generates a lot of needless labels and is inefficient. So it depends upon which product you are deploying in the network. For us, we have still those products which operate on an independent control mode, for which LDP generate labels for all the routes in the routing table, so which is a bit inefficient. So it's an additional protocol overhead. It consumes important control plane resources in the memory, not just your control plane, in your data plane also. Some of the states are created for some of the FECs, which are really not required. So LDP is a bit inefficient due to these reasons. On the other side, on the RSVP, the biggest challenge as an operator we face is RSVP scalability concerns. So as your network grows, number of LSPs grows, not just your head end, your mid part of the network, tail end part of the network, they carry the RSVP state. RSVP is a software protocol, as we know that. In order to fully mesh a RSVP-based network, number of LSPs scales to the square of number of Ps. We face problem when we add a new node in the RSVP-based network, so we have to create a RSVP mesh of this new node with the rest of the network. Same thing, we have to do vice versa. Second problem is with RSVP is that when we upgrade the capacity on the Ethernet side of the network, we have an ECMP scenarios. So by default, RSVP tend to stay on a single path by its own nature. So in order to circumvent those, we have to create a lag, which is essentially a logical link, or else we have to go back to our head-end routers and create new set of tunnels, which will traverse via the new path. So essentially, by using existing MPLS protocols, we face a lot of complexity in managing our legacy network design. So for our new network, we decided to go with segment routing, not yet an RFC, it's under a draft stage. So the reason why we went with segment routing, one is simplicity. So we have just one single unicast protocol for any services across the network. Second reason is that it's meeting one of our goals from a converged network point of view is that under a single network, we can now offer both flavors of service. We can route some services on the shortest IGP path cost, and we can leverage traffic engineering so that we can offer disjoint path to our customers. And that all too without running any additional MPLS protocol. So your IGPs are capable of providing those sort of functionality. Other reasons with going for segment routing is that it has solved all the existing problems of the LDP and the RSVP world. So while doing traffic engineering, there are no more scalability concerns. It's based on the concept of a source routing. There are no states anywhere in the middle of the network or tail end part of the network. Now we can leverage ECMP while doing traffic engineering. So we can use combination of node seed and adjacency seeds. So ECMP is no more a challenge while doing the traffic engineering with segment routing. No more concerns with the coverage. So segment routing is deployed using TILFS, which ensures 100% protection for any topology within the network. So the problem which we face with regard to the LDP is also taken care very well. It can interwork with existing MPLS protocol, LDP, and the RSVP, and it support all the services what we have in our network today. Some details on our SR deployment. So we have deployed segment routing on ISIS IGP, and we use IPv4 as the transport using standard MPLS data plane. So when we turn on the SR within our network, so we need to advertise one interface, which is essentially your router ID loopback address within the SR domain. And again, there are a couple of methods available how you advertise the labels on your loopback addresses. So far as we went with an index ID approach, and we configure the index ID as the last octet of the ISS net ID. So this ensures uniqueness within the network, and this ensures simplicity from deployment and operational point of view. sRGB range, as per the draft, ranges from 16,000 to 23,000, but we found that there was certain conflict with that range with one of the product which we are using in our network. So we went with a different range, 100K onwards, so that it's always remain exclusive from segment routing point of view. Label space per nodes, we have taken 65,000 labels, so that if we upgrade our network tomorrow, a node will never be full shortage of labels from a node point of view within the SR domain. TILFA coverage, so this is taken from one of the node in the network. So you can see that out of 2030 prefixes, we are 100% covered. So be it your high priority, medium priority, or low priority prefix, so everything is pretty much covered. So TILFA can provide 0 segment, single segment, and double segment protections. So by double segment, I means that it can intersect the P and Q node in case there is no common PQ node in the topology. So the problem which we are facing with the LDP remote LFAs is also taken care here very well, and this is evident from our topology that TILFA can provide 100% protections. The second thing what we are doing with segment routing is that we are integrating it with our existing IP network. So yeah, SR is fully interoperable with existing MPLS protocol. So in this integration, what we are doing is that we have IP network, so we have certain edge routers there. Those routers we are interconnecting with the core routers of the new network. So essentially the core router of the new network or boundary routers of new network, they run 2 protocols, LDP on the access side and SR on the new network core infrastructure side. And in order for this migration to work, there's a role of mapping servers. The job of mapping server is to advertise labels on behalf of known SR nodes, which in our case are legacy P loopbacks. So we advertise label for all the legacy P loopbacks within the SR domain. And mapping server concept are like router filters, so they can be either off path or in path. But for our deployment, we have chosen in path mapping servers, and we deploy these on our core routers. to maintain high level of resiliency, so that in case there is a failure in one of the core, traffic can, your mapping server advertisement are still available by the other core routers. So features working with this deployment for us are essentially layer 3 VPNs, internet services, unicast services, both V4 and V6 combination, and all this with the QoS functionality. And our use case for integration is that we connect sites from LDP to SR. We do vice versa, SR to LDP, and mostly we do LDP to LDP via the SR cloud. And it's indeed a seamless integration, and it's one of the working deployment for us. The third thing, what we are doing with segment routing is that we are working on segment routing traffic engineering. So this is an ongoing evolution in our engineering lab at present. So the model which we are going is a controller-based approach. So controller, as we know that it's an open source implementation, but in our case, we are not going with our in-house development. So we use one of the vendors' controller. And the main input to the controller is it needs the view of the topology. And again, there are bunch of methods are available how controller can get the view of the topology. In our case, it runs BGP link state with our route reflectors. So it sucks the link state database, and it gets the view of the topology. And our controller is a centralized controller since we are a single area network. So it's a centralized controller, and it's a stateful active controller. So it can initiate the LSPs, it can update the path whenever it is required. And we do have a backup controller also in case this controller fails, so traffic can switch to the backup controller. From process point of view, the orchestrator pushes the configuration on the head end, and then head end pass the request to the controller to calculate the path. Controller calculates the path, and it sends the path back to the head end, and then tunnels are formed. And all the tunnels in our case are on demand tunnels, which essentially means that a BGP process on the head end initiate the SRT process, and then dynamic paths are calculated. And the features which we are currently working are mostly disjoint path with node, link, and SRLG, and various fallback options. Let me talk briefly on the evolution we did on the services side. So on the legacy network service design on the IP network side, we rely purely on the BGP as our control plane protocol. So be it any services within the network, internet services, IPv4, IPv6, multicast, unicast, so everything is routed via the BGP. And for our mass scale deployment, we deploy this using route reflectors, and we keep separate RR for each service type to maintain high level of resiliencies and to maintain fast convergence within the network. On the Ethernet side of the network, we follow a different architecture. So access is purely layer 2. So we run standard Ethernet ring protocols on the access side, and on the core side, it uses full mesh of pseudo-wire-based solution, TLDP-based pseudo-wires. So we have like point-to-point pseudo-wires, multi-point pseudo-wires, and E-tree-based. So whenever we span a service from one city to other city, which goes via the core, so it uses core-based pseudo-wire-based solutions. Certain challenges we face with our existing service design. So currently we have a different implementation method for L2 VPNs and the L3 VPNs. So this adds a lot of complexity in the network. This adds complexity from provisioning point of view. This adds complexity from troubleshooting point of view. We have a different NOCs which manage the L2 VPN and the L3 VPN. Then there are challenges with the technology point of view view itself. So if you talk about VPLS, so in VPLS your control plane and data plane are mixed. So let's say there's any loop or there's any flooding in the data plane, so it impacts your control plane also. In the core, you need a full mesh of pseudo wires, so there are a lot of scalability concerns. And if a resident customer comes to us and he demands active kind of solution, so currently we can't offer this due to unavailability of this solution in the technology itself. So on the new network side, we decided to go with BGP as our standard de facto routing protocol. So the major paradigm change which we are doing is we are introducing Ethernet eVPNs on the Ethernet side of the network. So reason why we are going with eVPN is one is simplicity. So we can rely on a single protocol, BGP, for any services within the network. So be it your IP address distribution, unicast, multicast, MAC address, everything can be done via the BGP now. Core doesn't need pseudo wire now, so no more scalability concerns. BGP can provide fast conversion, so we can we can use some of the key features of BGP like BGP PIC file, L3 VPNs, which can provide fast conversions, and EVPN MPLS use type 1 AD route, which can provide the fast conversions. And this has also resulted in ease of configurations. This has simplified the operation and measurability of the services for our new network. Some details on the EVPN point-to-point services. So we follow the RFC 8214, and it's a next-gen solution for Ethernet VPNs. We have EVPN services in our access network from our AR routers to AR routers, and for our mass scale deployment, we deploy this using router reflectors. And it uses standard set of address families, AFI value 25 and AFI 70. And the data plane of the services is deployed using segment routing, so it leverages all the standard benefits of the SR on the data plane. And on the control plane, it supports auto discoveries. And for a single home customers, it just uses 2 routes. It's very scalable solution. It's simple to deploy, and it's a really scalable solution. Ethernet EVPN MPLS, which is essentially an ELAN services. So we follow the RFC 7432, and it's a replacement of VPLS. So it's similar to the L3 VPN. So instead of your IP address distribution, MAC addresses are distributed using this technology. And again, from deployment point of view on the access network, we follow a plain EVPN MPLS from our P router to P routers. And for our mass scale deployment, these are also deployed using route reflectors. Good point is that whether it's a point-to-point services or multi-point services, it uses same set of address families, which is AFI value 25 and 70. So from P point of view, whether we want to offer point-to-point or multi-point services, we just need one session with the route reflectors. Again, non-unicast are transported using segment routing, so it again leverage all the standard benefits of the SRs. And for our bump traffic, we use ingress replication method, which again use SR as the transport. One thing we are doing separately is that for our single home customer, we use non-zero ESIs. In this case, we don't need to rely on individual BGP MAC withdrawals. So it can use type 1 AD route for faster convergence. IP services, some details on our IP services deployment in our new network. So pseudo-wire headend is a feature. It just changed the termination point of the services within our network. So we terminate all the services on the core layer onwards. So this is a feature which hides the customer-facing interface with the underlying media of the access and aggregation router. So essentially, we use an MPLS-facing interface as the termination point of the customer services in our network. So as far as customer termination are concerned, so customer services still terminate on our access rings. And from there, we extend a layer 2 services, EVP and VPWS, which get terminated into the core routers. And from there, we bind this into the VRFs or GRTs that depend upon the service category. If it is a VRF VPN, it normally gets routed via the egress P router. And if it is an internet services, we keep it in global routing table, and this will be routed towards the nearest peering routers. So anything unicast on this new network, for IP services, we use segment routing. And if it is a multicast, we use RSVP from the core layer onwards. Network function virtualization. So as I mentioned initially that one of our goal for the new network is network function virtualization, considering various benefit of the NFVs. So as you know, it improves the scalability, it improves the performance of the VNF, it eliminates the hardware-based limitations, and it provides a lot of flexibility and agility that we can increase memory, CPU at any given point of time. So based on that, we are virtualizing various important network infrastructure components like route reflectors, PC controllers, DDoS controllers, and so forth. And as far as deployment is concerned, we deploy this on standard Intel Cross 86 based hardware, and we use dedicated VM for each network function. And we don't do any fancy stuff like cloud computing kind of things, so we deploy this on our own cold managed data centers. And we are doing our own in-house development, so we deploy this on standard Ubuntu machine on a KVM hypervisory. One example is route reflector virtualization, where we have successfully moved from a hardware-based RR towards an VM-based route reflectors. So currently we have 3 route reflectors in the network. One is for internet, second is for layer 3 VPNs, and third one is for Ethernet services. So we use dedicated VM for each route reflectors, and we follow a centralized design, which essentially means that we have deployed this route reflector in the 3 centralized locations, and each server holds 3 VMs. From IBGP client point of view, they form session with their respective route reflectors. For internet services, as I mentioned initially, that we follow hot potato routing in the network, and to keep a centralized design, we use stuff like BGP add path, BGP optimal route reflection to keep a centralized and then optimal route reflection within the network. Some experiences and key takeaways. These are the operational experience from our deployment. So with segment routing, all MPLS services are fully supported, be it L2 VPN, L3 VPN, VPLS, IPv6, and so forth. LTP-SR enter working, full multi-vendor support. So Cisco, Juniper, Nokia, they are our in-house, and it's indeed an multi-vendor seamless experience. We found certain bugs also. So one on the LDPSR side is that under some specific failures, so let's say there is a node failure, and in those scenarios, if your ISS prefixes doesn't have the TLFA backup path, then ISS stops sending the merge flag, and without merge flag, this is a then complete black hole of the traffic. And this was fixed by means of a patch. On the segment routing side, we found one bug which was quite often in our network, is that we have noticed inconsistency in the forwarding entries on the control plane and the line card. So the moment you have a failure, traffic switch to the TLFA backup path, and once it has to revert back to the primary path, so your control plane converts, but your line card stays on STL entries, and the moment traffic hits the line card, it results in the loop, or result is in the black hole of the traffic, which was again fixed by means of a patch. One limitation we found on the segment routing side is that it generates label only for the loopback addresses. So let's say you want to generate label for some of the connected interface. That feature is not yet available. So we need this because we connect various infrastructure components on our core network, and we carry their traffic as label switch path in our network. So again, this was fixed by using LDP-SR mapping servers. The biggest challenge on the segment routing side, what we are facing, is that it's not yet supporting the multicast solution. So some talks are going on for some of the solution like TreeSeed, which is a controller-based approach to offer a multicast solution. But problem is that at present only Cisco is supporting this. Other vendors are not supporting this. And BEER, which is a bit index explicit write multicast solution. So this has become a standard, and it has become a working group also. But problem is that there's a lot of hardware-based constraint, especially the Broadcom chipset. Yet they don't yet support the multicast solutions. While doing traffic engineering, we have noticed that maximum sit depth is a bigger concern due to the nature of source routing. So normally segment routing, when it has routed the service from the ingress to egress, it use the bigger label stack depth, and it's still a challenge for some of the Broadcom chipset. So this can be fixed by means of a solution called binding set. On the AVPN side, we didn't notice any interop issue. So be it Cisco, Juniper, Nokia, they all follow the standards. EVPN FAT is one of the biggest challenge which we are facing. So it's a feature where you want to distribute a single EVPN services, multiple flows across the multiple set of the core links. So that is not yet available. Hierarchical EVPN for the large network, this is still a challenge. So a lot of work needs to be done in this direction. Certain key takeaways. So single infrastructure for all services. This has simplified the transport and service architecture. So now we have a unified MPLS design, unified PGP service design. So this had added really lot of simplification in our network. It has reduced the cost, OPEX and CAPEX. So whether we want to upgrade a node or whether we want to upgrade the capacity in the network, we don't have to do this now in isolation. We have now one orchestrator, which is an automated orchestrator, and this has resulted in faster service delivery for our network. Benefit realized with next-gen MPLS technology for us is simplified design, deployment, and operation. And overall, next-gen MPLS technology is proved easy to deploy, maintain, and use. That's all from my side. Thank you.
Thank you very much, Amit, for that great presentation. It's always good to hear. It's rare to hear a segment routing implementation in actual operations, so appreciate your sharing of experience. With that, any questions for Amit? This session is webcast, so please do state your name if you have a question. Anyone? I just had one quick question.
Yeah, sure.
Just curious, I know Colt has acquired several networks throughout the world. I'm based in Japan, and I know you guys acquired 1021 there. Are you looking to integrate all your networks into your current new design?
Yeah, so that's the history of the legacy network. So
Yeah.
that we acquired various organization, and then we already have converged long back. So there is no more a separate network for us.
Okay,
Yeah,
so they're not downstream. You actually integrated
Yeah.
all your net.
So,
Okay.
Yeah, we have one network, one AS now,
Yeah.
including all those different components.
Okay.
Yeah.
Okay. Thank you, Amit.
Thank you.
All right. Thanks. And next we have Andre from Nick.cz going to talk about the bird routing daemon.
Excellent. Hello, everybody. My name is Andre Philip, and as it was said, I'm from a company called CZNIC, and I would like to talk about a software project called BIRD. Since you are all routing guys, I hope there must be some knowledge in the room, so let me abuse the situation. I'm standing in front of you, and can I ask you, please, who is using BIRD or has a good knowledge of it? Please raise your hand. It's not so bad. And who of you who raised the hand has some knowledge or tested BIRD version 2? Oh, we are 2 in the room. Excellent. Thank you for that. Okay. Okay. Let me start. Surprisingly, this project is very, very, I would say, ancient. It started in the last millennium. In 1998, it was we just met like 3 guys together. We were students at Charles University in Prague, and we were talking. It would be really cool to do some routing daemon. You know, please consider that time the only routing daemon on Unix machine was called GateD. I don't know if some of you remember that. It was really horrible beast. It worked, but it was very poorly maintained afterwards. So now I don't think it's used anymore. And we said, let's do something better than that. Let's do something that will be, you know, very flexible, very efficient, something completely new. So we wrote it. It supported some basic functionality. And as a typical students, after we finished the work and we got grades for the seminar work, of course, we didn't continue on that. So the project slept for a while. And with some small reincarnation when I submitted a few patches because somebody was really pushing me hard, so I had to do that. But then it slept basically about 10 years. And then it was reincarnated again in 2008, because that was the time where my company, which is called CZNIC, started a whole new department called CZNIC Labs. So I know it sounds a little bit weird. You know, my company, the main focus of my company should be administrating .cz domain, and it was really true till the year 2008, because that time we were, you know, domain name registry with a very small R&D department. I think now the situation changed dramatically. Now we are a large R&D department with small registry attached to that. So the main focus of that R&D department are open source software and open source hardware. I just put 2 logos there as an examples. Not Resolver, high performance DNS server, and Tourist Omnia. That's an open source hardware router which runs BIRD as well, of course. So the project goal at that time, we wanted to make an open source routing daemon, fast and efficient enough. You know, we wanted really to be the most efficient on the so-called market, to be portable and modular, and support the current routing protocol. And again, we are talking about 1998. That time, you know, IPv6 was starting protocol. Incredible, right? 20 years ago, and it's still not running. So we decided to include IPv6 support at the time. By the way, I think OSPF version 3 wasn't standardized at the time. What happened? What we achieved? we said it should be portable, which is sort of true. It's run mainly on Linux machines. Currently, we actively maintain just Linux and 3 variants of BSDs. But the layer that adapts to a Unix is pretty tiny, so it's not very complicated to port to other operating system. But at this point, nobody really requested anything else than Linux and FreeBSD. We support IPv4, IPv6 as a, of course, static protocol. We support router advertisement. We support BFD for link state checking. The 3 major routing protocol, RIP, OSPF, and BGP in many variants, and also a new protocol called Babel. By the way, is anybody using Babel here? Not really, right? It's a new thing. Then quite important thing which was requested by some of the network engineers, RPKR. What is different than the other routing daemons? It can run a multiple routing. It can handle multiple routing table. Some of them can be synchronized with the operating system, but it not necessarily has to be. So with this daemon, you can create multiple routers, root servers, root reflectors, just running one instance, and they might interact each other or not. I think I'll show you a picture later on. For that, we use protocol pipe, which is a protocol that connects to routing table and can do filtering and many stuff. We have very powerful configuration, which is a good thing and bad thing in once. The good thing is that we are really not tied with the classical configuration schema introduced by Cisco and other vendors. We use a configuration file when you can sort of write the configuration like a language. The good thing is that we can, easily express many fancy filtering features, much more efficient than the others. The bad thing is that you have to learn something new, which, of course, it's a painful. We have also a command line interface, but it's mainly for read-only operations. Of course, you can restart some protocol, but mainly it's meant for read routing tables, look at some route, whatever, show state of protocols and stuff like that. As I said, the configuration is in a config file, so whenever you change the configuration, you just reload it. There is very good kind of analysis that runs through the configuration files and really tries to find what changed. So if you just change a single parameter, it will reload the configuration and really just change the protocol that was affected by this change. So it restarts if necessary, but will not affect the other protocols. And also, some latency tracking, internal watchdog. It's a full-featured routing daemon. I specifically picked some BGP features. We support BGP community, standard, extended, and large, of course. We have capability negotiation, great for restart. As I think I mentioned, it can run as a root server and root reflector, especially the root server part is very popular by internet exchange points. It has a BGP multipath and add path feature. We support longer ASNs, but I think it's a standard these days, and also enhanced root refresh. All those features are related to version 1. I will explain what will be added by version 2 soon. Here's the picture I promised you. So this is Bird, how it looks like internally. This is just an example of configuration. You have some central routing table which can be synchronized with the operating system routing table, so forwarding table, I think I could say. And that routing table can be connected to multiple different protocols. I have like classical variant, static, OSPF, BGP. But, for example, you can have some reason to have different routing table with some other BGP protocols. So here's an example that those routing tables are connected with pipe protocol, and you can do some additional filtering there. Again, if your operating system supports multiple routing tables, there can be additional synchronization, or doesn't have to be. It's really very flexible because this is just a simple example, but especially some of the exchange points create very, very complicated scenario with a lot of routing tables that have a very complicated way how they synchronize each other. Here is the example. I promised you to show. As I said, the configuration file looks more like a C program, I would say, at least because we have those fancy, I don't know, is it parentheses, the right word for that, those symbols. On the other hand, if you are an experienced engineer, I think you will easily recognize what this means. There are some global options, then we have some protocol definition, some protocol-specific configuration. This is for static protocol, this is for BGP. Again, something that you could easily recognize. And that is the thing which makes the configuration so unique. This is the filter language. And I would call it filter language because it has all the parameters of languages, and this even can include some functions and stuff like that. Here is an example how the command line interface works. This is a very simple example. It just shows you which protocols are running, when they went up, when they went down. You can, of course, look at details of each different protocol, which has a specific information, and yeah, very simple example. This is an example that shows the routing table. As I said, you can have multiple routing tables, so you can add a parameter. This is just for the default one, but you can have more of them. So here is how the routing table is organized. You can have multiple routes per prefix, and so on. And you can also specifically show the routes for a specific protocol. This is an example that you just filter those that are related, inherited from OSPF. And here comes the beauty of the CLI. There are multiple ways how to kind of filter the output. One way is just to show the most specific routes for single IP addresses. You can use predefined filters. For example, in your configuration, you predefine some filters, and you can check from the command line if what it does in the current routing table. Of course, you can count the number of prefixes. You can check what routes are exported to a specific protocol. So again, this is just a subset of the main routing table. And here is a little bit taste of the filters. So this is how you can write that this IP address is subset of the networks, and this IP address belongs to two routes, the default one and loopback. And this is the way which is a little bit complicated, but if you are experienced enough, you can write even filters into the command line interface. So here's again the same thing, but written a little bit more complicated way. So now I would like to kind of show you an example where this is especially a good thing. This is a root server policy. I chose a simplified root server policy from the Prague Internet Exchange Point, XYZ. And if you use a root server, it's hard to define your routing policy. It's not easy to say I don't want to peer with this one, I don't want to peer with that one. So that's why this mechanism was created. You add some BGP community to your root, and the root server reacts according to this policy. I just chose a very simple example. In reality, in our exchange point, this table is much longer, much more complicated. But if you signal 0 and peer IS, this route is not advertised. If you add some AS number of the root server, this is advertised. If you add 0, do not advertise to anybody, and this symbol advertised to all. And this is checked from top to bottom. So with this, you can either say ban those networks or export the route just to those networks. And here, how this is implemented. If you know, for example, how this can be implemented or configured in Quagga or Cisco, it's a lot of lines, per every exchange point member. But in BERT, the implementation are just those. I think it's 7 lines. No, it's a very basic function which has parameters. So again, you can see that this is really a kind of programming language. This is just to not use anything that didn't come from BGP, probably not important line. And then you just say, if it's 0, don't export. if there is the signaling export, and if it's this symbol, don't export to anybody, and the default is true, and that's all. Again, if you know how root servers configuration look on other platforms, they are much more complicated. This is really beautiful thing. And again, I show you we have variables and we have also some constants. And this is how the configuration looks for a specific member of the exchange point. Again, local ASN, neighbor IP addresses, and then you just call two functions, and that's all. Really very simple. So a little bit about the filtering. This is how the filters are written. We have this is an example of a prefix set, which you can see can be not just a simple prefix, but you can check all the longer prefix of certain lengths. I'm just using examples for IPv4, but IPv6 looks similar, and this is how you avoid that filter list. The same thing, you can have a set of AS numbers, and again, if you can just allow certain AS numbers in the path, and this is best example because this shows you the case control statement. So you can, for a specific AS number, for example, you can have specific filters, and you can call them. What this means, the filters are compiled into bytecode. They're executed later on. We can use variables, sets, constant. We have very rich data sets, including mainly which you would expect. So IP prefix, some enumeration, quad of something, set of something, and also we have some very specific types, for example, for community list, extended community list, and large community list. Then we have some operators, again, mainly taken from programming languages, so something you would understand. There's a special one called ROE check, which is for our PKI operations. And then we have control structures like if, else, case, and you can call functions, again, with variables. And everything you saw, those structures, those filters are usually implemented with some weighted balanced trees. So it's very efficient, usually in logarithmic time complexity. So it's very fast, and that's why it's so popular, especially in companies that do a lot of filtering, which is, for example, exchange points. And one more, this is a protocol example. Template example that, of course, you can do some templates. You just define how a regular peer of a route server should look like, and then you have a specific instance which you just inherit those variables, and you can also redefine them. The default is limit of 50,000 prefixes, and it just warns, but for the specific you want it to block to stop the BGP session if it reaches this prefix. It's just example. I don't say this makes sense, but just to show you that you can inherit all these. You can inherit templates into the protocols. So this feature set makes BERT mainly popular, as I said, for the companies that do a lot of filtering. I used to maintain this slide, but I don't do anymore because basically up to 9, according to a records of EuroX, 2/3 of exchange points worldwide are using BERT as a root server. So I stopped maintaining this page because it was too much. Many companies change logo there. It's really sorry for that. Basically, mainly exchange points use them. Some CDNs. I think Netflix is an example. Of course, we use it in our tourist route as well. As I said, very popular by mainly exchange points and CDNs. So everything I said now was about version 1, and the latest is called version 1.6.3. Here's the list of the recent features. but I think they were all, they were all described described before. This release went live more than a year ago, so it's a very well-tested release, and as I said, used by many exchange points. So recommended if you want to have the first experience with BERT. It's a rock-stable release. Although we made a new version, which I will introduce later on, this will be maintained for a long time. We are preparing some version 1.6.4 with small fixes. And maybe some additional features. So if you want to build something long term, this is the best version for that, especially for root servers or any root refactor, anything. Very well tested release, really recommended. So what's new in version 2? Maybe I haven't mentioned, but that's an important thing. BERT's architecture that time, and again 20 years ago, was designed the way that you compile the daemon with option IPv4, and it had all IPv4 protocols. Then you compiled the same source code with option IPv6 and created a new daemon, new binary, which supported only IPv6. So those versions were separated. Although it was, compiled from the same source code. If you wanted to support both families, you had to compile two binaries, and they were not interoperable. It was basically because we optimized the routing table, so IPv4 just took care of IPv4 routing table and IPv6 of IPv6. It was a limitation, especially for multi-protocol BGP and also for some other protocols we would like to add. So that's why, and that was the main driver for making a new version, version 2. It was released 2 months ago, so it's a brand new thing. As you saw, there's not many users yet, so that means if you're going to use it in production environment, be a little bit more careful. On the other hand, we did major redesign. This is the version for the future. We will build on this code, but again, it's not yet tested well. So if you want to help us, please test it. Please try to deploy it in your testing environment and send us any feedback. Any feedback will be welcome. What's new in that version? Currently it's 2.01. As you can see, most of the new features are related to multi-protocol BGP. With that integration, we could add all the address families and secondary address families, FE-SAFE. So we could add. We could add BGP multicast, we could add full spec support. We finished completely the RPKR support. I will show you some example of the configuration. MPLS, MPLS VPN, VPN 4.6, 6P, all the stuff is implemented. We added BGP configuration, and also this is just how the default configuration of BGP should look like now. It's a small thing. So all this is implemented in the version 2. Again, you just compile this once, and you have a binary that support all those AFIs and SAFIs. Here's some example of the configuration. If you remember the previous examples, there's the major change that you have a protocol definition, and then you just have specific paths for IPv4 and specific paths for IPv6. We call this channels, so we have two channels, and one have IPv4 has some different filters. You can also change the routing table for IPv4, and the same applies for IPv6. Again, those things can be very independent, but this is multi-protocol BGP, so you can run all the families. This is another example which is extended to all the other AFIs, SAFIs, MPLS, VPN6 multicast, and this is example for full spec. So just how the configuration was extended. There is an example of RPKI. We support both SSH and TCP transport. So this is an example how you transport ROS through SSH. You have to use some sort of authentication, of course. connect to some server which provides it, and then there's a way how you filter using RPKI. That's the operator ROA check, which I mentioned earlier. This is an example of flow spec record. It's there's a lot of variables you can tune. So this is just an example. Again, I don't say this really makes sense, but just to show you the flexibility of the protocol. There's one warning. BERT supports flow spec, but it's not synchronized with Linux root kernel. So it may work like a reflector. It may work like a source of flow spec records, but it's not implemented the connection to the Linux kernel, so or FreeBSD kernel. So just be warned. So that was just a taste of the version 2. So what happened next? It really depends on our supporters. This is open source. We are giving it for free. So to get some money, we have companies that have some support contracts with us, and they are paying us money. And of course, they have a right to say what should we do. So we will see what they need today. If you want to join that club, I will be more than happy to talk about it, of course. But those companies have usually very high pressure, or they really would like to improve the BGP efficiency. So that will be the main target for the next period, to shorten the convergence time, responsiveness, and also optimize the filters more. And then in a little bit longer future, we would like to implement ISIS. Again, we couldn't implement ISIS with version 1 because ISIS requires the integrated address family, so that's why. And I repeat again, if you are using 1.6.3 and it works for you, perfect. If there will be any bug and so on, we will maintain it, so we will provide new versions, don't be afraid. So that's us. If you are interested, test it. If you will test version 2, please provide us feedback. Would be really great. There is some URL to the website, and if you want to know more about the great projects we do at CZNIC, just check labs.nic.cz. Thank you very much.
Thank you very much, Andre, for that great overview. Open the floor now for any questions for Andre.
Hello, Alexander Azimov, Kyoto Labs. First of all, I'd like to thank you for supporting the BERT version 1 and for finally launching BERT version 2. It's really, really important for our company. And at the same time, I have a question related to the flow spec rules. First one, I was surprised that in the example that you showed on the slide, it's in a static protocol. Why?
Well, because you need to define the entry, and then you can export it to BGP. In BGP, there is no way to create it, right? So it's kind of special routing tables designed just for this. And if you want to generate those routes, you have to prepare it somehow. This routing table cannot be synchronized with the operating system kernel, so it's just more virtual thing.
Yeah, I've got it, but I'm surprised that it is not just a separate protocol.
Well, that's a good point. We were discussing that, and since we have more routing tables for different AFIs, this was like kind of logical things to make to have it nice and defined the same way as the other address families.
And another question also related to flow spec. I recently tried to find any documentation on the website related to flow spec, and I wasn't able to find any.
Oh, really? That's weird.
Yeah.
Because
maybe I was not so good in search, but still it seems to be hard to find it.
So maybe because you didn't check the static protocol, maybe that's the reason. So if you will look at the static protocol, you will see example how the flow spec is defined.
I was just using keyword flow spec and BERT in Google, and I was able to find only one page with and there was any description where I should set up rules.
Okay. So if you can send me just an email, I will send you the pointer. And another good way is to join the mailing list where you can ask. There's a lot of supportive people that have a very good experience with that. But definitely, especially this example was taken from the website, so it is there.
Okay, so never mind. Thank you.
Thank you.
Thanks. Anyone else have any questions for Andre? Oh, sure.
Hi, this is Safi from Equinix. It's just a comment here, so I have two questions. So one, when we're using the bird daemon, so do you have any feature like auto command completion? Because every time you have to
Which feature? Sorry, I didn't catch it.
commands auto completion, tab completion. Or,
Oh, I
yeah,
see.
it's like other
In
vendors.
command line interface, yes,
Yeah.
but the configuration is done in a normal text editor, so there's nothing like that there.
Okay.
But in command line, there is something like that. Yeah.
Okay, so the question is, you mentioned that you have a config change in 2.0. So do you have any internal tools if you're going to upgrade from 1.63 to
Not yet, but we know very well that this should be done. So I promise we will make this, of course. Yeah.
Okay, thanks. Thanks a lot. Bye.
Okay, we have time, I think, for one more question if anyone has a question for Andre. Okay, thank you, Andre.
Thank you.
Next, we have Christian from Interland IX. He's going to talk about the TVX multicast exchange point that's built over the Interland IX infrastructure. Christian?
Hello, everybody. My name is Cristian Copcea. I'm coming from Romania, from the Internet Exchange. Recently, I mean in 2016, we started a TV exchange using multicast and the actual infrastructure used by the Internet Exchange Point Interland. As you know, normal IP channel distribution is consisting of a resection hub, a terrestrial IP network, a CATV headend, and then it goes to the end user using all this stuff, all this kind of equipment. What we are doing here is using our TV channel, multicast flows, and then to the client by the means of provider TV stations. Why should you use an exchange point to make a TV exchange? It is very simple because you have a very efficient channel distribution. It is highly reliable. You are maintaining the same equipment for both services. You can also build redundancy by using the Internet Exchange as well as another means of transportation. Unconstrained transmission bandwidth, the ability to deliver from the simple single definition up to UHD, 3D, HDR. Usually, any Internet Exchange point is hosted into a colocation facility where TV providers already exist. So it is very easy to talk to them and to make interconnections. This is how you get also the lowest latency possible. What I wanted to talk, in fact, it is not about the TV exchange itself, which is trivial, let's say, but about the management platform we are developing at Interlan, which is a high security and offers full control over the operators that are receiving streams. Using this content management platform, only the content provider can allow or restrict the access to the stream towards the cable operator, even if the software is hosted by the Internet Exchange Point on one virtual machine. The TV operator will always know that he is the only one able to start or shut off the streams for the client. Every time somebody makes an operation, everybody is notified by email. The actual implementation is done via a cron job that takes the access rights from a database and translates them into equipment ACLs. And it depends, Cisco, Arista, whatever everybody is using into the IXP. Something that I didn't write here is that the TV operator has the ability to inspect the code that is injected into the equipment. This is for a full transparency. And of course, in case of emergency, somebody goes wrong, there is a technical staff that can be contacted to take necessary actions. This is one page of the management platform, and anyone can check what cable operators are using the stream at any time. Every action on the management platform is also journalized. It is also easier to publish all the TV operators into the management platform, and anytime a new TV broadcaster is added into the platform, he can contact the operators directly from the management platform. He doesn't have to look for contact information. What's the cost? The cost is free for all. It is a win-win situation. Those connected to the Internet Exchange Point are getting for free the TV stations. Now, for free is from the Internet Exchange point of view, because the TV broadcaster, like HBO or other broadcasters, may ask for something in return, but it's not our concern. We are giving away for free. What are we getting in return as an Internet Exchange point? It's simple. We are selling ports. Each time somebody is connecting to a new stream, 1, 2, 3, 4, he will need capacity, he will need ports. And he will be required to buy those ports from the Internet Exchange point. This really works. We have connected 29 TV stations in 17 months without too much effort. The IXP also became more appealing. People started to look for us, not only for the TV content, but for our primary business, which is selling peering and ports. I had yesterday the acceptance of the Interland's board to say that all the management platform will soon be released on GitHub. It will be free for all to be used. Again, also with the TVX logo, which is not related to anyone, and it can be related, in fact, to everyone who is using or who will use this this idea, this management platform. These are the logos of the operators of who were connected, operators and TV stations. Thank you for your attention. If you have any questions.
Thank you, Christian. Interesting presentation. Anyone have any questions for Christian? I just had one quick one. The participants, are they all in country? I can't tell by the logos. I don't recognize all of them. But are they providers in Romania, or is it regional, or does it matter?
Actually, most of them are providers in Romania, but we had a very strange request from a Croatian TV station. I don't know if I'm right in what I'm saying, but anyway, it is not a Romanian one. And he asked if he can join the IXP. What were the conditions? Well, it's the same condition as for everyone. Just we said you have to be physically in Bucharest. No problem, no problem. Okay, the second issue is that you cannot inject unicast into the internet exchange if you want to publish your TV station. No problem, I will come with my own equipment. And actually he's transcoding from unicast to multicast exactly before entering the internet exchange. So it can be really international.
So as long as they follow the requirements, it doesn't...
Yes,
okay.
yes.
Right. Thank you, Christian.
Thank
Anyone
you.
else have any questions? Okay, so that's the end of the session. We ended about 20 minutes early. Thank you, everyone, for joining. I do have a quick announcement. There was a loss of some reading glasses. If anyone's missing any pair of reading glasses, and a bag of pashminas. I guess those are, if you're not aware what that is, like a cashmere scarf. Someone left a bag of pashminas there, so they're at the registration desk if you lost anything, if you lost any of those, or you know anyone that does. So, okay, thanks again, everyone, for joining. The next session will start in another 50 minutes or so. Thanks.